So we're going to do a little bit of review of what we did last year and then add on to that learning a bit. So very quickly I'm going to go through some of this because you should be familiar with this, and in fact this should be in your formula booklets. So you may want to take a second and check to see if that's true. So when we were learning sequences and series, we were learning about both arithmetic and geometric. Arithmetic being where we're adding and geometric where we were multiplying. So there were some formulas that we learned last year in grade 11. So term n is equal to a plus n minus 1 times d, where d was the difference between the terms. And for geometric, term n was equal to a times r to the power of n minus 1. And you should also remember that the geometric series we built on, that was our exponential function, and we did a lot of stuff with that. For the sum of, or the series, an arithmetic series, there were two formulas. So the first one, and maybe you can fit that inside the box. I'm not even going to try. So S of n, or S subscript n divided by 2 times 2a plus n minus 1 times d. And that was if we were given certain information, then we could use that. So if we knew the difference and we knew the starting number, then we could come up with that value. If we didn't, but we knew the first and last term, then we had our other formula, which was n subscript n's, right? So n subscript n equals n divided by 2, and then what we were doing was adding our first term and our last term. And so that allowed us to determine information about the series, given we could solve for n, we could solve for d, we could solve for a. So given certain information, we could come up with the sum of a series, a sum of an arithmetic series. The sum of a geometric series, S subscript n, is equal to a, where a was our starting value, minus r to the 1 minus r to the power of n all over 1 minus r. And with this particular sum of series, we did some applications in grade 11 that included things called annuities, where you were receiving a regular monthly payment, and that was an example of a geometric series. So these should be very familiar to you. If they're not, then you need to revisit your grade 11 books, if you kept them, or notes, and familiarize yourself with these formulas. So in this example here, we're being asked to identify whether the following series is arithmetic, geometric, or neither, and give the next three terms in the sequence. So when we look at the first one, we see that it's the squares. The next values would be 25, 36, and 49. This is neither geometric or arithmetic. We're not adding or multiplying by the same value. This next one, minus -4 to -1 1/2, it looks, we're not adding or subtracting the same value, the same difference, but what we are doing is multiplying by -1/2 each time. So -4 times -1/2 would give me +2. +2 times -1/2 would give me -1. So this is going to be a geometric series, because we're multiplying by -1/2, and the next three terms would be -1/4, +1/8, and -1/16. Okay, I'm just going to clear this because I need the space. I'll just erase this now so I have more space for the next one. All right, term subscript n is equal to 3n minus 4, and we're starting at n equals 1. So if n equals 1, then that means that our first term is going to be negative 1, because 3 times 1 is 3 minus 4 is negative 1. If n equals 2, then we have 6 minus 4, which is 2. And if n equals 3, we have 15 minus 4. What happened here? If n equals 3, sorry, it's 9 minus 4, which is 5. And when we look at this, you can see that we're going up by an even number, which is 3, so this is arithmetic. Okay? The next example, find term Tn, or T subscript n, term n for the following sequences, and find the indicated term. So we're being asked for this one to find the 21st term, but we first have to know if it's geometric or if it's arithmetic. So we look at the first 3, and it looks like they're going up by 3, so that would be an arithmetic sequence, and we're going to use the arithmetic formula, which is T subscript n equals a plus n minus 1 times d. So for term 21, we know that a is our starting value and it's 2, and then n minus 1 means that we're going to multiply by 20, and the difference for, I'll carry on. The difference between them is 3. So that's going to give us an answer of 62. Now, what if now the question said, okay, now tell me what term 22 is or what term 19 is, and now we have to go through this whole process again. So one thing that we can do is find a general term or a general expression for all terms and then use it to solve. So let me show you what I mean. So again, starting here, T of n is going to be equal to a plus n minus 1 d. So T of n, our general expression, is going to be 2, that's our starting value, plus n minus 1, and then the difference is 3, and we can simplify that. So we have 2 plus 3n minus 3, or just 3n minus 1, and then we can use that to solve for any term, including term 21, and we can see that 3 times 21 would be 63 minus 1, which is 62, so that gives us the same result. The next one here, we're starting at negative 4, ending up with positive 16, and then from 16 to negative 64, you should recognize that those are, that we're multiplying by 4, so it's geometric, and so we're going to want to use the geometric expression. So our a value for here is going to be our starting value, which is negative 4, and then r, which is our rate, the rate that we're going up by is by negative 4, because the sign is alternating. So then term 6 is going to be negative 4 times negative 4 to the power of 5. And since they're both the same base, this is a degree of 1. It's the same in this particular case, and only because they are the same base we can add those together. So it's the same as negative 4 to the power of 6. You can't always do this, but in this case it works out nicely. And that is going to be an answer of 4,096. I won't let me draw it. There you go. Okay, for this next question, it says that we have a sequence where term 3 is 18 and term 6 is 486. We're being asked to find the general term for T subscript n if the sequence is both arithmetic or geometric. So we're being asked to do both. So if it's arithmetic, we know that we're going to use this formula. Okay, and we have, we want to write the general expression in a way that will allow us to solve for whatever n, the value n is. So we have two unknown variables, a and d, that we need to solve for. And we're given two pieces of information. So we're going to use this first and plug in the values for term 3. And term 3, we don't know what the starting value is, but we do know that it's 3 minus 1 here, and we don't know what the difference is. So we have a plus 2d. Okay, and we also, so we can rearrange that, and we know that term 3 is equal to 18. So I'm going to rearrange it in terms of a. So a would be equal to 2d minus 18. No, sorry, it's the other way around. Whoops, sorry. Minus 2d plus 18. All right. And then we also know that term 6 is equal to 486, so I'm going to plug in values for that. So I have 6 minus 1 is equal to d. This is 486, and it's equal to a plus 5d. And when I rearrange that, I get 486 minus 5d is equal to a. And then hopefully you see where I'm going with this. The next thing I'm going to do is set, since this is equal to a and this is equal to a, I'm going to set each of these equal to them, each other, and solve. So I have negative 2d plus 18, and I'm going to set that equal to 486 minus 5d. And now I'm down to an equation of one variable, and I can solve for d. So this will give me 3d is equal to 468, and so d is equal to 156. And then that will allow me to solve for a. So I have, I'll use this, and when I plug that in, negative 2 times that d value will give me 312. Negative 312 plus 18, so I have a is equal to negative 294. So given that, I can now write my general expression for the arithmetic series. So that will be t of n is equal to a, which is negative 294, plus n minus 1, times d, which is 156. So t of n is equal to negative 294 plus 156n minus 156. So I'm going, oops, sorry, I missed the n here. So I have 156n minus 294, so that's 300, 450. So that will give me the term, any term given the value of n. And now we want to look at the same question, but this time, what if it's geometric? So if it's geometric, we're using t subscript n equals a times r to the n minus 1. And we're given the same piece of information, that term 3 is 18, so I have 18 is equal to a times r, sorry, r2, oh my goodness, sorry, times r to the power of 17. And, oh sorry, it's been a long day. Our n value for this one is 3, sorry, so r to the power of 2. And then our second one, 486, equals a times r to the power of 5. So I'm going to use a ratio to to solve these. So I have a to the r to the power of 5, and a times r to the power of 2 is just going to be equal to 486 over 18. And then this will simplify very nicely. These divide out, and we know what happens when we are dividing exponents, we subtract. So I have r to the power of 3 is equal to 27, and so r must be equal to 3. And then when we sub that back into either one of these expressions here, and the first one is easiest, r squared would be 9, 18 divided by 9 is 2, and so we have an answer of a equals 2. And so when we go back to what our original question was, and that was what's the general expression for this, we can just plug in these a and d values. So now we have, in place of a here, we have 2, and in place of our r, we would have 3. Okay, this next question here is asking us to find the sum of this following series, and we have to show all of our work. So we look at the series and we can see that we're missing some values in the middle, but we are given our first and last term. And if you look at the values, you can see that they're going up by positive 6. So we know that there's a couple of things that we know that we want to start capturing. So we know that our first value is negative 57. And we can see that our difference is 6. We know it's arithmetic. And we've been given the first and last term. And we have a formula for when we're given the first and last term for the sum of a series. And if you look at that formula, the one thing that we need to know is how many terms there are in the series, and we don't know that information. So before we can solve for the sum of the series, we have to first know how many terms there are in it. So what we're going to do is go back to our original equation for solving for terms in an arithmetic series, and start to plug in some information and see if, okay, can we figure this out? So 27 is our last term, so I'm going to plug it in. I don't know how many terms there are, like which term number this is, but I'm going to use 27. I know the a value is negative 57. Again, I don't know how many terms, but I do know that the difference is 6. So now I'm down to an expression with just one unknown, and I can solve very easily for that. So I'm just going to gather all of the numbers to one side here. I have 6n minus 6, so that'll be plus 6 when I move it over. And this is 6n. And so that just gives me a value of 90 equal to 6n, and so n must be 15, and that means that there's 15 terms in the series. And then I can go and use the sum of a series formula for arithmetic series, which just uses the first and the last term. Okay, so we're told that there's 15, we now know that there's 15 terms, and we know that the first term is negative 57, and the last term is 27. So that will give me an answer of negative 225 for this series. So you have to know these formulas, and you have to solve for the unknown so you can start to do the sums of series. Okay, the next one, when we take a look at it, we can see that we're not adding or subtracting an even the same number. It's going down by a third each time. So 27 times a third gives me 9. 9 times a third gives me 3. So my a value for this series is going, my first term, sorry, is going to be 27, and my r is going to be a third. We're given a formula for the sum of a geometric series, and that formula is a 1 minus r to the n all over 1 minus r. Again, do we know the number of terms in the series? We do, because it's asking us up here to find the sum of this series, and the subscript tells us how many terms there are, so summing the first 8 terms. So that means then that the sum of 8 terms is equal to 27 times 1 minus a third. Oops, that looks like a half. 1 minus a third, and the third is raised to the power of 8, all over 1 minus 1/3. When you do this on your calculator, you will get some kind of crazy number, and so we're going to round this, and it's approximately 40.49. Okay, the next question asks us to find the value of x such that 5 plus x, 8, and 1 plus 2x are consecutive terms. So the key with this is the word consecutive. It means that they come one right after the other. And we're also told that it's an arithmetic sequence, so that makes it really easy too. So if they are one right after the other, then 5 plus x comes just before 8, and since it's arithmetic, we know that there is some value that we are adding to it to get to the next one. So if we simply take 8 and subtract away 5 plus x, that will give us the difference between our two terms. So 8 minus 5 minus x is equal to d, and so that gives me 3 minus x equals d. And then I can do the same thing for 1 plus 2x. I'm going to take 1 plus 2x, and I'm going to subtract 8 from that, and that should give me the difference as well. And so you can see that 2x minus 7 is equal to d. And then we're just going to take those two values and equate them, because they're both in terms of d. So I have 3 minus x is equal to 2x minus 7. And so that gives me an answer of, let me see, 7 and 3, sorry. So 7 and 3 is 10, and I've got 3x on this side, and so x is going to be equal to 10 over 3. Okay, the arithmetic series 1 plus 4 plus 7 plus ... all the way up to term n has a sum of 145. How many terms does the series have? Well, we know that it's arithmetic, and so that makes it really easy for us. We want to first capture some information. So we know a is 1. We know that the difference is 3. And we have a couple of formulas for sum of an arithmetic sequence. But the second equation that we have means that we know the first and last term, and we don't know that, so the only one we can do is this one. Okay, now we don't know n, but we know a and d, and we also know that this value here is 145. We've been given that information too. So n over 2 times 2a plus n minus 1 times 3. Okay, we can start to simplify that, and so I'm going to run out of space very quickly, so go ahead and start to simplify, and then I'll post the solution here. Okay, so hopefully you've gotten to this point, and I'm assuming that you're starting to see what's going to happen. We're going to cross multiply here and end up with 290 equals 3n squared minus n, and hopefully you understand what the next step is. And you understand that you're going to need to solve this quadratic. Now, I'm very good at factoring, and there is no way I'm going to waste my time trying to factor this, so I'm going to try and solve for n using quadratic equation. which is minus b, which is minus negative 1, plus or minus b squared minus 4 times a times c, all over 2 times a. I'm assuming you can do this math all right. What we're going to end up with is x is equal to 1 plus or minus 59 all over 6. There are two possible answers, so either x is going to be equal to 60 divided by 6, which is 10, or x is going to be some negative value, and that is not a valid solution for this. So our answer will be x equals 10. Okay, so now we're going to start looking at sums to infinity. So the idea where the value just keeps increasing and increasing and increasing. We're summing just a never-ending list of numbers to infinity, and we're trying to understand what that sum might be. So if you take a look up at the top here, the idea of a sum of a geometric series, at the top in the numerator there you see 1 minus r to the power of n. So if r is between negative 1 and positive 1, in other words, if it's a fraction, then as we raise that fraction to an exponent that becomes bigger and bigger and bigger, the expression of r to the power of n becomes so small that it's virtually zero. It just gets to be such a small, insignificant number that we say that it's approaching zero as it goes off into infinity, as the fractions get smaller and smaller and smaller and smaller. So the summation, or the sum of the geometric series, goes from being this expression here to this smaller and more simple expression here, because that whole expression of 1 minus r to the n, where r to the n approaches 0 or becomes 0, just means that you have a times 1 over 1 minus r. And that's where, for values where r is between negative 1 and positive 1. So here's our first example here, where we have a half plus a quarter plus an eighth. So you can see that that r is a half. We're starting with a value of a is a half, and as we multiply a half times a half, we get a quarter, and a quarter times a half, we get an eighth. So our r is a half. And so what we're looking for is the sum of this geometric series, except that we're looking for the sum to infinity. So according to our formula, it's a, which is a half, all over 1 minus r, which is 1 minus a half. So a half divided by a half, which is just a half times 2, which simplifies to 1. So as these fractions get smaller and smaller and smaller and smaller, we expect the sum of this infinite series will become 1. Okay, the next one, we're just given it in sigma notation, where it's saying it's varying between 1 and infinity. We can see that the r value, or first off, let's just declare that a is 1. That's our starting value. We're starting at 1 times a quarter to the power of, or negative a quarter, and then r is just negative a quarter. And if I were to write it out, it would look like this. So negative 1 quarter to the power of 0 plus negative 1 quarter to the power of 1 dot dot dot. So you can see that why the a value would be 1, because this first expression here is just 1. So we're looking for the sum of this infinite series, where a is 1, and on the bottom we have 1 minus our r value, which is negative a quarter. So we're left with 1 divided by 5 quarters, which is the same as 1 times 4 fifths. So the sum of this infinite series would be 4 fifths. Okay, these next two questions are really kind of fun. What rational number has the repeating decimal expansion 1111? And the idea is that these are repeating values. So this number, repeating, I want you to think of it as it's a sum of a series of numbers that look like this. And so on off into infinity. So if that's the case, then we can see that it's going up by a multiple of 0.1. If you multiply 0.1 times 0.1, go ahead and do that and see what you get. So 0.1 times 0.1. And if you do it again, you'll get the next value. So we can see that our starting value is 0.1, and then the rate that we're going up by is 0.1. So then we can figure out from there the sum of this infinite series is going to be our A value divided by 1 minus our R value. And that's going to give us 0.1 divided by 0.9, or 1/9. And then if you go ahead and divide 1 by 9, you'll see that it gives you that repeating decimal expansion. So we can make use of this sum of an infinite series in this way as well. The next one says, identify the rational number q whose decimal expansion is 1371, and there's supposed to 0.1371, and there's supposed to be a sign over the point over the 71. So the 71 is the repeating part. So let me explain to you what I mean by that. So what that looks like is this. We have 0.13 plus, and what we're adding to that is 0.0071. That's the repeating part, plus 0.000071, because it's repeating like this: 13717171 ... Okay, and so this is continuing on into infinity. So there's two pieces to this, and what you're supposed to see is this is the part that's our repeating sequence. So there's some value that we can multiply the first one by to get the second one, and the second term by to get the third, fourth, fifth, sixth, and then this one here is kind of on its own. So I'm just going to deal with this part here first. We can see that we'll just treat it as the sum of a sequence, or sum of a series of numbers. So our first number is going to be 0.0071, and then if you, sorry, just a sec. Sorry, so if you take this value here and you divide it by this value here, it will give you the rate at which these values are going up by. So that gives us our R value of 0.01. So we can use that information to get part of our answer. Okay, so what we have is our sum of an infinite series is equal to, there's our A value, and then we have 1 minus our R value, which is 0.01. And this is going to simplify to 71 over 9900. So that is the sum of this series just for this part of the expression, but we still have this piece here that we have to address as well. So we know that we have the first part, which is the 0.13, and we can write that as just 13 over 100. And then we have the second part that we just solved from the sum of our infinite series, which was 71 over 9900. So I'm just going to add those two together. They should give us the value we're looking for. And when we simplify that, we get an answer of 1358 over 990. And if you go ahead and use your calculator to do that division, you should see that that's in fact the decimal expansion that you were expecting to get, this answer here. So that concludes the series review and sequence review and sum to infinity. You should be able to do your homework, and this finishes the unit, so you need to start preparing for the test.